worries. Thanks, everybody. Tonight, I'm just going to present a little bit about ultrafine analysis. So LabWest has been doing it for a number of years now. And so we thought we'd just present some data and some information about it and see how it goes. So we've already done the acknowledgement. So LabWest partnered with CSIRO back in 2017 on a project looking at ultrafines and the analysis. So Dr. Noble and Anisha Henny were still are the two major drivers of the project. The project's started in 2017 and it's moved on in a number of phases where it's become a bit more of a commercialised methodology that LabWest offers. But CSIRO are still doing quite a bit of work behind the scenes with research and looking at machine learning models and using computer systems to aid in the interpretation of the data. So CSIRO have quite an extensive website with a FAQ and as well as a number of other resources that delve a lot more into the science behind this methodology and what's required with their next generation analytics, so all the machine learning models. I'm not really going to present much of that tonight because my talk was more about the practical applications of it, particularly for the industry. But yes, there's a lot more information online if people want to go back and have a look a bit further into it. So at presentation outline tonight, I'm going to talk about the science and the history, just a brief overview, the practical aspects and the versatility of the method, so why this method works, we believe. And then we'll just have a bit of just a quick run through about some industry uptake and some success outcomes. So the science and the history. The methodology has got quite a thorough backing in terms of science behind it. And there's been a number of papers written about the different aspects of the testing. And it also, the whole lot of the project in the first couple of years culminated in the production of this report through CSIRO, which gave a bit more of an overview. So if we begin now with basically what are ultrafines, because that seems to be the catchphrase that everyone sort of says. It's the one that we use, me and Blake, you know, when people say ultrafine samples. But what does that actually mean? So ultrafines are actually clay particles in a soil sample, and they're the ones that we're looking to analyse because they're acting like a repository of mobile elements within the regolith. So we're looking at the particles that are called clay in a soil sample, and they're generally less than 2 micron in size fraction. There's been a number of studies over a number of years where people have used finer and finer fractions of soil samples to try and enhance targets and pathfinder elements, all with the idea of being able to drive an exploration program straight from a surface soil. That's, I guess, the holy grail. So there's been a lot of them from CSIRO, a few people from other industries as well, other countries, where they looked at a variety of different fractions, and they might be 10 micron, 53 micron, 25 micron, and then we are looking now at the 2 microns. So the history was there. There was a theory that, you know, utilising these things, and that's where CSIRO started and picked that up as a driver of a method. So why the clay fraction? Now, clay is a bit of an ubiquitous term because it means basically what the size fraction is. And a lot of people talk about clays, but then clays can have mineralogy, so different minerals can be clays as well. So you can get a number of clays in samples, you know, including like your kaolinite, smectite, illite, all those type of things. But that's an important part of the sample. But the other important bit is that clays have a cation exchange capacity. So that means they have an ability to gain a charge and then it's a negative charge, and then you've got positive ions within the regolith that might be mobile moving around, are attracted to these clay particles, and so they stick on the clay. So if you take the clay out of the sample, you'll also be taking out the mobile ions that are actually attached to those clays. The other benefit of using a clay sample is that it has a very high specific surface area. So that means that you can easily increase your sampling statistics because you've got such a large surface area. You can decrease the number of samples that you are taking because each sample can now represent quite a large volume in the regolith. So back when we started the original method, we looked at firstly we looked at extracting the clay, and then we looked at how do we analyse it. And we went through a number of different things. And this is where the rigorous part of the science comes in. We looked at microwave assisted acarejia digestion. We looked at just a plain acarejia digestion, a weak acarejia digestion, hydroxylamine hydrochloride digest or leach, which that one was for selectively targeting manganese oxides. And then there's also our multi-acid digest, the 4-acid digest. So it was a pretty comprehensive look at all the ways that we could actually analyse this clay. And at the end of the day, we all ended up with method number 1 was the most robust and appropriate and cost effective and all those sorts of things. So that was the optimal method to use. And the project itself ended up with this famous map. I guess it's a famous map. It's the one Ryan uses all the time. It's one of the original maps. And it shows that the data at the top was a number of samples taken and then just analysed via conventional 25 gram for 30 gram acarejia digestion, normal soil sample, just total soil. And then we re-ultrafined all of those samples. And now you can see that the detection limits go down, the signal is enhanced in response. So now you've got a lot more targets being generated from the same number of samples. So that leads us now into a bit more of information about practicality and versatility. So basically, when you're trying to take a sample, you've got objectives in taking a sample, and you want to look at the consistency of sampling, eliminate any organic matter, eliminate large rock particles, and you want it to be an easy thing to do. I think one of the examples I heard was that often if you've got a field assistant out in the field digging holes, the holes at the start of the day are probably nice and deep, and by the end of the day, they're perhaps not quite as deep. And so you end up with a bit of inconsistency over your sampling. So we wanted a method that would be robust and easy to use. So it became a practical taking of practical samples. And you can see there, all you really need is a couple of high-tech scientific equipment. You need a shovel, you need a tray, and you need a sieve. And that's all you need to go and collect the soil samples. The whole idea of screening is to remove the coarse rock because we're only interested in the fine materials. And so it's simple enough to screen at 2 millimetre in the field. And you can use just a kitchen colander even. You want the sampling part is you need it to be practical. So you're looking at constant depth. And it only needs to be, it could be 5 to 10 centimetres. Ideally, you want to select the same soil horizon, which in this case, we're looking for the B, the subsoil, which has the sand, the silt, the clay. We want to remove the organic topsoil and organic matter and just sample the subsoil. So often it can be a relatively easy thing to do, as in it can be reasonably obvious. And the other benefit is that the sample size. So now we only need 200 grams or about a cupful of sample to do a test. Whereas previously to do soil assays, you might have been taking a 2 or 3 kilo bag of soil back to the lab. Now the benefits of that are huge because now all of a sudden, 200 samples, 500 samples can fit in a backpack or a small box. The transport costs of the lab are you know, a lot easier. It's a lot easier for the lab to handle as well. So, yeah, so you only need about a cupful of a sample to analyse. When we get it back to the lab, we run a hydrostatic separation process on it to take out the 2-micron fraction, separate it from the rest of the sample. And it ends up being, at the end of the day, a very small sample like this. Generally, most soil samples, depending on you know, how clay rich they might be, you would generally get about 1%, 1 to 2% clay in the sample. So from our 200 grams of an initial sample, where you know, we've got plenty of fines available. It allows us now to be consistent with our sampling as well, so we can cover samples that might be rich clay to relatively poor clay. We can, because we only need a relatively small amount. We then do a microwave digestion on it. So microwave acarrhea is our standard method. So obviously, I've given presentations in the past about microwave digests and what the advantages are, and that's why we use microwave digestion. But the basic come away is that the samples are all individually sealed, so you get no cross-contamination, which is a big, huge benefit. And also, because we're running at high temperature and pressure, we can get a very efficient extraction of the elements that we need to do. So they're the two big winners. And we finish up with an ICP-MS finish. So you end up with just a solution, which we then run on the ICP-MS. Now, the ICP-MS is brilliant because that gives us a versatile element suite. So what it means is that when you do an ultrafine analysis, we're actually doing a 53 element or even a 64 element suite, including rare earths. So you can do a comprehensive look across a whole region, and you'll get all the pathfinders as well as your target elements, as well as other ones that you might not be looking for as well. So it's a very comprehensive package. Quality controls, we put quality controls in where we can, and the tricky thing is, because it's a new technology, trying to work out what sort of standards to put in. Most of the time we are using you know, commercial soil type standards. You're wanting to look for, you know, relatively barren samples, so we don't put high grade gold samples in as QC standards, but you want to do those type of things. And that leads to another bit of a drama, because we're using microwave digestion, and it's a lot more efficient, a lot more higher recovery of the elements. Now, when we compare a commercially bought standard with that's been certified using a typical acarrhea method, the microwave digest gives us more recovery. So you end up with results that now are a bit more higher than what you would get for your acarrhea. So you have to be careful there. And you'll see just the high ones I've done in bold of what our working values are for the microwave digestion. And you can, so there's obvious ones there, like rubidium, for example, on OR45F. You know, see there, a conventional acarrhea is 14, whereas the microwave acarrhea is actually getting us around 25. So that can be a little bit of a trip for young players, but we provide this sort of data now. We've been analysing microwave digests for a number of years, well, 14 years, and we've got some really pretty robust data on this, so that helps with that. Other quality controls we've been developing as well, where we're basically taking samples from projects and combining them and producing like a reference standard, so the material that we can use. And this material is now exactly the same as what we're actually analysing. So we don't need to extract it, and it just is its ability to be. It's come from samples, real samples that have been homogenised, and we use those as well as quality controls. Another benefit is that you can actually use historical pulps, pulps that have been pulverized. And you do have to, you will increase the 2-micron fraction because of the pulverizing action, will do it. But in large part, you'll get a little bit of dilution, but you won't get, the overall signature is going to be retained. And we've done a few tests that show this. So if you have a look here, I've just got a couple of slides which I'll go through relatively quick. Well, I'll just discuss this one and then we'll move through the others. But you can see here that we're getting similar sort of responses up and down on the conventional soil UFF, which is in the dark blue, as opposed to the UFF process being done on a pulp. And so we're getting sort of similar response. And it's in a lot of other elements as well. So now we'll just flick through some other data. So I've got a few squiggly lines to have a look at. This is now just a bit of an ultrafine comparison to a standard soil aquiregia digest. And so you can see here that one thing, the most obvious thing, and this is gold, is that the ultrafine response is a lot higher than what the soil response is. It's enhanced. And the benefit of that, and this goes on to the Kingston map sheet, is if we now, this is the raw data, and if I apply the detection limit for the soil, the WA25, you can see there that some of the numbers are now starting to fit in within the soil. And if we say, right, okay, let's do 2 times detection limit, which is probably valid there, all of a sudden all of our numbers are starting to end up in the 0. And that's basically what we were seeing on that Kingston map sheet, where using a conventional thing, the anomalies were not showing up. But now you can see it on the ultrafine, it is actually being much more well-defined. And you see the same with other elements. So the example here, in the same case, the ultrafine is always in orange and the aquiregia is in blue. We're just getting an enhanced signal. Trend patterns roughly, around about are staying same, but the response is a lot more higher. So you're getting more certainty in that response. So what about other techniques? Right, okay, so let's have a look now, a quick look at some ultrafines versus a partial leach. Because partial leach technology is one of the ones where it's for a long time it was thought it was going to be a holy grail, but for some reason it tends to come and go. And we'll just have a look, we'll compare them. This case here we go. We've got the partial leach in the blue and the ultrafine in the red, in the orange. And you can see there that the pattern is roughly the same. So we're getting quite a good thing. We're getting an enhancement. That's the thing here, is I've actually plotted this data on different scales to line the maps up. So the lines are all in the same spot. But the partial leach on this side, we're getting a maximum of 10, whereas on the ultrafine, we're picking up as a maximum of 50. So it's a much stronger anomaly. You can see there in platinum, once again, platinum is increased by a factor of 5. Palladium's gone up by a factor of 5. Platinum's gone up by a factor of 20. And other elements are all the same. And the numbers are significant, the response is significant. So let's, now, we were always talking about, we use the aquiregia digest as the main method. And then the questions was early on was, well, what about using the 4-acid digest? Now, the 4-acid digest is a total digestion. So what it's actually doing is dissolving up all the clay that's in the sample. It's not necessarily preferentially stripping those mobile ions off the clay particles. It's going to dissolve everything up. So the 4-acid digest will have its place where your sample has lots of particles within it that might be resistant elements. So for example, if you are, say, looking for rare earth elements in a xenotime-rich environment, you might be better off using a mixed acid digest, because some of those 2-micron clay particles are actually going to be possibly xenotime type minerals. So in which case then you'll probably do want to dissolve the whole lot up. But if you want to do just normal reconnaissance, then it's not necessarily required. But let's have a look at just some response of a 4-acid digest versus aqua regia digest on the same thing. And so you can see here that the patterns are the same, but you do get some divergence. So you see here beryllium, there's a bit of a shift in the ultrafine versus the mixed acid digest. So the mixed acid digest is increased quite a bit because now we're dissolving up part of that. We're actually dissolving up all the clay. So it's not just the mobile ions that are attached to the clay. So lots of squiggly lines. So another thing that I've noticed with when doing these ultrafines now, we've picked up quite a, because we've been doing the numbers for a number of years now and looking at a lot of different data. I noticed this little thing. I thought it was interesting, so I thought I might just sort of share it with some people. It's got to do with rare earth element signatures. So back in 2023, ASRA were looking in the Yilgarn drilling for carbonatites. And so they've been actual drilling, these are drill rock samples. And they were looking at ionic clay style mineralisation. And so they prepared this little explanation which shows that about the distribution of rare earth elements within an igneous rock. And so basically the rocks show that if we plot these spidergrams of the rare earth elements, you're getting a smooth transition between them. And europium has always got a little bit of a bump in the road there. And then as you move up through the regolith towards the zone, through the weathering, it finds that the cerium is actually mobilized more. So you end up with a depletion as you tend towards the surface, as opposed to an enrichment down further. So by looking at the plot of your rare earth, you can actually see where within the regolith you actually are. And as you transition between fresh rock and say ionic clay style material. So if we look at, whoops, wrong button. So if we look at some ultrafine samples now, one thing that we can see is the europium bump is actually quite clearly defined in the middle there. But then if we look up the top here where the cerium is, we're seeing exact same signature within the surface soil sample in the ultrafine. So it's related in some way. Now, I guess this sort of thing is something that could be exploited in terms of exploration type thing, because we're seeing a bit of a behaviour in the ultrafine at the clay at the surface that's sort of behaving similar to as you might expect as if you're digging out rock samples at depth. So I just thought that was a bit of an interesting little thing to illustrate. One thing that I've noticed. One thing that Lab West is doing as well, I haven't got any data to present today, but we're starting to look at some isotope signatures as well. So we're looking at things like lead isotopes, sulfur isotopes, and strontium, potassium type isotopes, and seeing what we can read those isotopes with our ICP-MS. It's all about seeing what, if we can produce the data, what can it show? So that'll come in the future and probably maybe next talk one day. So industry uptake and success. And of course, this is all about how do you define success, because a lot of people define success in a lot of different ways. One question we always get is that when did someone take an ultrafine sample and build a gold mine from that one ultrafine sample? And the answer is that's not how it works, as everyone knows. So it depends on your definition of success. So now, I've defined all of these as a success. So we have actually analysed samples from more than 250 clients now. So like I said, since 2017 when we started the project, 2019 it became a bit more commercialised. 2021 it took off, and so now it's a regular thing we do lots of. We've done over 510,000 samples using the Ultrafine method, and Blake generated some maps, and it shows where we are. All of these sites within Western Australia and Eastern Australia, and now the world. And we're starting to get samples from Africa, obviously, Northern Europe and Japan off the side of a volcano, and also New Zealand as well through some glacial till areas. And all of those areas have all been promising. If we have a look at on our website, we've actually got a page called ASX Releases, which Blake curates. And in that, we basically keep details of all the different companies that use it, where they report a success. Now, a success is not necessarily a mine, but a success means that they're driving value into their company because they're finding something and they're actually doing something to lead to something else. So it's all about the layering. So if we have a look at Hamlin Gold, their announcement here, they use the geochem from the ultrafines and it maps out targets, allows them to define things to go and look at. CGN Resources, same thing. They've picked up gold enrichment with the soils. But the other thing is that in their announcement is that the pathfinder elements, the silver, arsenic, bismuth, all sort of trend towards suggestions of iron ore, copper, gold type mineralisation. So this type of stuff is I believe it's a success because it's actually found something and it's leading to something else, and so it's driving the industry. WA1 is another one where they're generating heat maps from of potential areas. Caspian Resources, once again, this technique was always developed initially for gold, but now it's being used for other elements because you're getting such a versatile big element suite. So you're picking up nickel, copper. So anomalism, and we're Zuleika. Mount Claremont, this is some Marquee Resources, and this one is antimony. So Pathfinder is antimony and lead. Iceni Gold, they did a lot of work. In fact, they did a whole exploration tenement with Ultrafine, covered the whole lot, and it gave them some brilliant sort of data and lots of follow-up information. If you have a look at Iceni's list on our website, I think we've got about 15 different releases, all relating to different areas with that. It was very comprehensive and very good. And of course, rare earth elements. So this is Summit Minerals, and their release is all about the rare earth occurrences. But once again, it's using Ultrafine. So basically, in summary, Ultrafines it's a robust, scientifically tested method. It's got a very practical and versatile workflow. Taking the samples is relatively easy. The sample sizes are small, so the costs involved with all that generation of your initial sample to do a quick reconnaissance over a prospect is actually not, it's not too bad. And it's being used by industry. The uptake has been very good and it's leading to successful outcomes. It just depends on how you define success. So it's all about the layers, adding to the layers. Thank you, everybody. If everybody's got a question, I'm happy to take a question. Otherwise, yeah, thanks a lot.